Yeah. Yes.
Our next speaker is Srimoyee Sen from State University. First confinement.
Can you all hear me? Or? Yeah, I guess. Okay. Thanks very much for organizing this workshop and inviting me to give a talk here. So as you can see, two of my collaborators are in the audience, Alexi and Theo, and then Larry Yaffe is also a collaborator on this work. So this is something I've been working on over the past probably now 4 years. So we have some new results, which is in preparation, and you hopefully see in a few months. So with that, let me get into the talk. So I'm talking about gauge theories here, the ones that exhibit both confinement and Higgs regimes. So, so let me quickly tell you what I mean by confinement here. So if you took the gauge sector of the theory and removed any mass that you had in the original theory, the theory should still exhibit confinement. That is, all the gauge fields are gapped. So that's what I mean by confinement. And what I mean by Higgs vaguely is that if you add the matter sector back and then somehow are able to condense the matter sector, it will give mass to the gauge fields, and that's what I mean by Higgs. So this is sort of the sort of hand wavy picture of what I'm talking about, and then I'm trying to make it more concrete. That's what the aim of the talk is. I suppose yes, that's what I would say. Yes, yeah. These are, I'm going to stick to, yeah. Okay, so there's a standard lore in the community inspired by Fradkin and Schenker. So the standard lore is the following. It says that, let's say you have a gauge theory that exhibits confinement. So let's say your matter sector, so your matter sector is in the fundamental representation of the gauge group. You could take scalars. And let's say you are dialing a parameter in the theory. For example, the mass squared parameter of the fundamental fields. And so you go to a regime where you have kind of confinement, to another regime where you have Higgsing. And if there is no global symmetry, which changes realization as you go from confinement to Higgs, then there's no way to tell these two apart. Okay, that's the standard lore, and that's inspired by Fradkin and Schenker's work in 1970s. So what I'm going to do in this talk is that I'm going to tell you that the results of Fradkin and Schenker hold in the class of theories that they work this out. But there is another class of theories where you would be inclined to apply the same intuition that you would be deriving from Fradkin and Schenker, but those don't apply. So that's what I'm trying to get to here. So here, I'm showing you 2 + 1 QED. And so here, the example that I'm showing you, there is a phase transition in this model. So you have a gauge field sector. This is a abelian gauge field. This is charge 1 matter field. It has a mass squared parameter and a quartic interaction term. So here, if you dial the mass squared parameter, if the mass squared is sufficiently negative, then phi condenses. So you are in the Higgs phase. And and the photon is gapped, right? And then if mass square is very positive, then these fields are heavy and you have an ungapped photon. So clearly there is a phase transition between the Higgs and the non-Higgs side. And this is, of course, expected because there is a symmetry that changes realization as you go from one to the other. It's the U1 topological symmetry. So that is spontaneously broken in the mass squared positive side, and it's not broken in the negative side. So there's a phase transition here, but there is no confinement in the mass squared positive side. This theory is, or what I mean is that there's no linear confinement in this theory, right? So now, so the point is that Fradkin-Schenker doesn't apply in an obvious way to this example because there's a symmetry that changes realization as you go from one regime to the other. But now let's introduce confinement here by putting in monopoles in this theory. And when you do that, the photon becomes gapped and you get linear confinement. And then there is no symmetry that changes realization as you go from one side to the other. And so Fradkin and Schenker applies here, and there is actually no phase transition separating the two regions. So this is an example, which is a concrete example of Fradkin and Schenker. But now I want you to do the following. I want you to tweak the original theory slightly. So what I want you to do is to add a spontaneously broken global symmetry to both sides, the so-called Higgs and the so-called confining side. Again, there is no reason to expect a phase transition from symmetry principles because you're adding this sector to both sides, okay? And then I'm going to tell you that there's going to be a way to tell the two apart when you do this. Now, before I go there, let me quickly tell you why I'm considering this such a strange model. It's because of QCD. So it turns out that QCD at finite density exhibits something like this. So in QCD at finite density, baryon number symmetry gets spontaneously broken, and you have a superfluid phonon at finite density. So that's why I'm doing this. So this is how to tweak the theory. So you have this standard gauge field, U1 gauge field. This big D is 2 plus 1, so this is three dimensions. I have two charged fields. One of them has charge +1, other has -1. MC squared is the mass parameter for these two fields. Here, I have implemented a symmetry between the plus and the minus field, so that's why they have the common mass squared term. Similarly, there's a common quartic term as well. And then on top of this, I'm going to add a neutral scalar field to this problem. So that's phi naught. There's a corresponding mass squared parameter. I will dial this mass squared parameter in such a way that this phi naught gets condensed. So this is going to give me my spontaneously broken global symmetry. Now, on top of that, what I'm going to do is to couple the charge fields to this phi naught field. Okay. So this is what this is telling you is the global symmetry in question is such that phi plus and phi minus have charge 1 and phi naught has charge -2 under this global symmetry transformation. So you can keep phi naught condensed and then dial the charge mass squared to go from a region where these two are condensed to a region where they are not condensed. So that would be going from Higgs to confinement. Okay, so now in this case, you can consider vortices in the phi naught field, right? So you get superfluid vortices. So now what happens on the Higgs side? So on the Higgs side, phi plus and phi minus have vacuum expectation values. And if you have a vortex in the phi naught field, this cubic term tries to create a vortex in this combination field, phi plus and phi minus, okay? And so now on the Higgs side, that means that either the plus field or the minus field will have a vortex. So then phi naught vortex becomes a flux tube, right? So this is a gauge vortex. So now let's say you want to compute a Wilson loop around this phi naught vortex. And if you do that, it gives you a phase of pi. So it's stuck at -1. What happens on the confining side? On the confining side, naively, what you can think is that plus and the minus fields are heavy, so you can sort of integrate them out. So you just have a vortex in the phi naught field. Now, if you compute the Wilson loop around this vortex, you're supposed to get a phase of 0. Okay, so these are not flux tubes anymore. So if you looked in more detail, you would see that there's confinement and string breaking. That's really what is going to give you a phase of 0. So, so you can see now that there is a way to tell the two apart, the Higgs and the confining sides apart. Question is there a phase boundary? So clearly we have a sharp distinction between Higgs and confinement. Now, before I end the talk, I want to give you a little more details on this, how to get to this Wilson loop being 1. So in principle, in the continuum, it's very hard to do a calculation, but you could formulate this theory on the lattice and try to do a strong coupling calculation on the confining side. So this is something we do, and the paper is not out. We're hoping that it'll be out in a few months. So we do this in the Villain formulation. Here I'm showing you the neutral field sector. So this kappa is the VEV, corresponds to the vacuum expectation of the phi naught field. And so this is the neutral sector. And then I have the gauge sector here, and these are the charge field sectors. And you go to a regime where this coupling is strong, and you can then compute the Wilson loop, and you can explicitly show that in the strong coupling limit, there's no phase on the confining side, and there's a phase in the Higgs side as you go to the other limit. So with that, I'd like to end. So here's the conclusion. We have shown that there's a sharp distinction between Higgs and confinement regimes of this type of gauge theory, where you have this spontaneously broken global symmetry on both sides. This is relevant for dense QCD. What next? Well, we want to locate where exactly this transition is. So we did a calculation, a strong coupling calculation, which is valid in very strong coupling limit. And then we have the Higgs side, but we want to locate exactly where this transition is. And so we will have to simulate this on a lattice and see where that transition is. And then we want to understand what's the order of this transition. And there are many other questions to think about. So with that, I'd like to end. Thanks.
So let's go to questions. We have does not seem like a problem. The condition on the board, there are conditions where you have the main wall, the turbulence the main wall. That wouldn't expect anything in the bulk of that. All low energy occupation but when you put the vortex, you could also consider the example model where you put a S1 growth in 36 and stuff. And then you would have the main wall, and this would be a transition on the junction of the domain. Not in the south. Why do you think it's the transition of the south?
The example that you're connecting to, I don't think directly relates to what I am talking about. So the domain wall example, there the two sides of the domain wall are actually in different phases, right? They're not.
No.
So that's a different example, I think.
So what I would think, the example I'm thinking about is, let's say you have massive parts of young males that they go high. There's a spontaneous breaking of mass one flavor, and then you dial the mass of the parts all the way to 0. There's no phase transition at all. You know, when you have very light one part, there's no Wilson movement or anything. Period gap in the bulk all throughout. But on the domain wall, Srimoyee and Cyber on this paper shows that there's a transition on the domain. If you can study in the large end, at least there's a almost massless and there's a transition on the domain wall.
So you're saying that the two sides of the domain wall are in the same phase?
Yeah. So But you can have a transition on the domain. On the domain, there's a TQFT with.
No, because you are going from one phase to another phase, and there's a transition on the wall. That is, it's a function of space, right? There is a transition. So the two regions are not in the same phase. But I don't think that's relevant for what we're doing here anyway. No, the two sides, you have two bulks, right? You have one bulk on one side of the domain wall and another bulk on the other side of the domain wall. Those two are not the same phases, right?
You can show that there's some non-local work, let's say, tractable. There could be two interpretations. So one possibility might be true. There's only a bulk. It could also be told there's something happening in the fall. And you can only tell that it's it'd be not shocking after all. Exactly how you see it. A priori, like you have to.
Okay, I'll make a prediction. You will not find any position, phase transition.
Well, we have already previous work that in some quarters of energy condition.
Yes.
Does happen in regime where people are under control that the actual bulk phase position precisely for the position in the storage.
But is it a phase transition? Because you're
It's
saying.
Yeah,
first order.
it's a first order phase. That's right.
And the question is that a phase boundary, then that everywhere in the phase diagram, but that, you know. I agree a priori, right? But they're not. I think you should take capital.
Yeah.
Well, it's more of a comment. First of all, I completely agree with you with the transition between the Higgs and confinement phase. And I completely agree that there's some degree with spontaneous development. Where I disagree is that, first of all, I think we probably disagree on what the symmetry is. And I think the order parameter is a non-local one. And you can often have transitions, not thermodynamic transitions, involve non-local order parameters. In this case, I think singular transition type of order parameter. Second thing I think is that the physical distinction between phase and fixed confinement has to do with the physical distinction of confinement type. On general grounds, the spectrum of the theory is always going to be gauge variant and color neutral, in fact. Nevertheless, there is a distinction between confinement. There's a type of confinement in the confinement phase, which involves essentially, well, I would have to define it, but it has to do with the formation of trajectories, the formation of fluxes, even if they break.
Mm-hmm.
You can describe this thing in a definite way. That's
Right.
distinct from what happens in the Higgs phase. So there's a physical distinction between the two phases. And there's also a symmetry distinction between the two phases. And it can be shown that the transition between the different confinement types coincides
Right.
with the distinction with the transition between the types of symmetries. It's not a thermodynamic transition.
Well, so the limit where we calculated, there is a limit in 2 + 1D where you can show that there is a transition. So it's possible to do it in 2 + 1D because you can write sextic terms in the phi field, in the scalar fields. So there you can show that when you dial the charge masses, you have a first order transition, as Alexei was pointing out, and it is a thermodynamic transition there.
In general, even in frequency. General in say lattice field and Higgs field. You can go continuously with the confinement phase to the Higgs phase without a transition. But there is actually a transition.
Okay, so that's a little bit different from what I am showing here, because what we have seen so far is that if you add this global symmetry to the theory, then the arguments of Fradkin and Schenker actually don't apply. So the continuity argument that you would have thought that would smoothly connect the two regions, that doesn't apply here. Okay, so So there's no reason to expect in this case that the two regions would be smoothly connected. Okay.
There is transition.
Mhm.
Wow. You move out of it.
Okay.
So maybe take the question. Maybe because I two questions about lanes. If it would be like a, a syntonic monopole in this case, stuff, I think that there could be a change in the situation because of maybe the global synergy would be not supported. So you see that it could be different dynamics. I guess when this type of instantaneous transition is included, like you see, like very on charge non-conservation and and it's related to this kind of, in this case like a blame and possible like so how this you approach would react to this additional part.
So, yeah.
We already added.
Yeah. I think he wants to add the monopole corresponding to the U1 symmetry of the phi naught field, which
Then we can break the global symmetry.
yeah, we don't want to do that, right?
Well, yeah, you could build in. You could just remove the global symmetry in the first place. So that one knows that we don't apply, but because there's kind of stability in adding up this type of transition. But imagine there is a period like that. Could argue it's not obvious. But suppose if there is, certainly if you destroy something in the model, yeah, that's fine. But it would be natural to first get as much symmetry as you can, and only then. But that seems like extra, like it's making it more complicated. No. But if you cannot state this without like by informal use, it's a if you're seeing your conducting is not quite resolved, breaking is one inside. So I think we should.
Yeah.
Again.